All right, the last video was running a little long, so I wanted to give a moment for everyone to grab their calculators so that we can do this last problem together on rate graphs. And this is going to be a calculator heavy problem, so definitely have your calculator. There's very little that we actually have to do in terms of differentiating or integrating here. We'll mostly need to set up and make sure that we understand what we're finding in the context of the problem. So we've got a human person. I don't know why I wrote that. It's pretty repetitive. If you're a human, you're a person, and vice versa, but it's what it is. A human person is filling a bathtub in order to bathe. Again, that seems kind of repetitive. I don't know why else you would be filling a bathtub, but I don't know. Let's just go with it. A human is filling a bathtub and opens the faucet at 6 p.m. The rate at which the water is entering the tub is modeled by this function b of t. So make sure we understand b of t is giving us the rate at which the water is entering the tub. And the unit is going to be gallons per minute. So I'll just highlight that, gallons per minute. So first question, how much water is in the tub at 6:05? Well, that means 5 minutes have passed. And in the context of this problem, what we're effectively finding is how many gallons do we have in the tub at 6:05? Well, from our previous lesson, we know that if we're given a rate function, then what we would want to do is integrate that rate function over that interval to find the amount that has passed, if you will, or the amount that we now have. So if it were velocity where we're given feet per hour, the integral of that would then give us the amount of feet traveled. In this case, integrating b of t from 0 to 5, so 5 plus 1.5 sine of x squared over 20. This would give us approximately 27.793 gallons. So that's how much water is in the tub after 5 minutes. Part B. If the tub's fill line is at 50 gallons, will the bath be ready by 6:10 p.m.? Explain why or why not. Well, we're basically asking ourselves how much water is going to be there by be in the tub by 6:10 after 10 minutes have passed. And will there be enough water to meet that 50-gallon mark? Well, let's look at that. So from 0 to 10, I'm going to integrate the same function. So again, 5 plus 1.5 sine of x squared over 20. And I realized in my previous problem, I didn't write dx, which we should do. This is a function of x. Apologize about that. When if you integrate that, take a moment, enter that into your calculator, make sure that you're pretty comfortable doing so, and hopefully you found 53.917 gallons. And so we can then say, yes, the bath will reach approximately 54 gallons by 6:10. So it will be ready. Okay? All right. Now let's try this last problem here. When the bath is over and the plug is pulled, the amount of water remaining in the tub is modeled by E of t. So again, E of t this time is a little different. This is giving us the amount of water that remains in the tub. It remains in the tub, and it's a function as a function of time. Now, as the water empties, is the rate of change of the water emptying, speeding up, or slowing down? Describe how we know. So we can say the following. The rate of change of the water emptying is, and pause the video right now if you need to and think about this. What would it be? The rate of change of the water emptying is slowing down. Because if we look at E prime of t, that actually increases. The derivative of E of t, the derivative of the function that gives us the amount of water remaining in the tub, that's actually increasing. Okay? With that said, the water is still constantly draining. So if you look at E of t is going to, we're looking at E prime of t actually increasing. So that is Another way of saying this, because I know this seems somewhat counter, we can say that less water is being emptied as time passes. Okay? So hopefully that helps with this particular problem, and you're a little bit more comfortable now using your calculator and making sense of the area underneath rate graphs and context to certain word problems. And if that didn't help, if that last part is still a little confusing for you, we can still go ahead and just try to graph that function here real quick. So we would say, let's just go ahead and enter in that function. Let's enter in e of t, and we'll write this as 50 minus 22, the natural log, we'll just say natural log of t plus 1, or I can just say x plus 1 here. And let me just kind of zoom out on this. Okay, and we're doing this over the course of a certain amount of time. Now look at this function here, okay? And if we call this here f of x, I know we call it e of t in the problem, but we would call f of x here. And then we were to graph f prime of x. So we can compare the derivative to the function. So we can say f prime of x. All right. Now, so just so we can really make sense of this, e of t represents the amount of water that's in the tub. Because we're draining the tub, we can clearly see that the amount of water is decreasing here. If we graph e prime of t, though, which I have modeled here as the blue graph, f prime of x, we see that that is increasing. Again, so think about this in context. If e prime of t is increasing, we could say the rate at which, because e of t, again, is giving us amount, the rate at which this water is emptying is slowing down. The rate at which that water is emptying is slowing down. So hopefully that helps make a little bit more sense of that last problem.